Hello, dear audiences. This is the part 6, episode 6 of Statistics and Probability for Engineers, and I am Mohammad Momenzadeh. Previously, we discussed about the axiom of the probability, and we used combination and the counting techniques that we learned to calculate a question, the probability of an event. So today we want to extend our discussion to discuss about the additive rule and the remaining parts. As you can see over here, we have some topics: the conditional probability, multiplication rules, and relation between multiplication rule and conditional probability. And if we have a time for this episode, we will go to the Bayes rule. I think that it's going to be in the next couple of hours that we will discuss about the Bayes rule. So we start our discussion by the additive rule. Let me just bring the slide of that one and discuss about that things. So as you can see over here, we have the additive rule, and this additive rule is totally based on one concept on a set theory, and based on that things, if we have the subset of a sample space S as A, B, and C, there are three subsets over here. We consider the first and second one, A and B, and as you can see over here, if we want to count the number of the elements of A, then this shaded part is a part A. It's a part belongs to A, and if I just add the number of the elements of A with the elements of B, then the intersection part is repeated 2 times. So to avoid the problem from that things, the number of the elements in a union is equal to the number of elements of A plus number of the elements of B when I remove the number of elements of their intersection. Based on this definition or these techniques, we can say that the probability of their union is equal to the probability of A plus probability of B minus probability of their intersection, and this is the base, the additive rule. So means that for calculating the additive rule, which is used for the probability of their union, we have this formula. I want to emphasize about the union and intersection and say that when we have the union of two sets, we have the words or to make the connection between these two events, and when we have intersection over there, we use a word and. Means that the first event gonna be happen and the second one. So the additive rule say that the probability of their union is equal to the probability of the first one plus probability of the second one minus probability of their intersection. And of course, if A and B are mutually exclusive, they are disjoint, or their intersection is equal to empty, then that intersection at the right side will be removed, and we have the probability of A union by B equal to the probability of A plus probability of B. This can be considered as one condition or one formula to say that in which case they are mutually exclusive, means that the vice versa can be true as well. So if we have a mutually exclusive events, then their union, the probability of their union is as the same as the addition of their probability. Indeed, the part C is as the same as the discussion that we had it in the third part of the axiom of the probability. So in the axiom of the probability, we just gave this situation for sequence of the events. It's not only true for n times of the events. I mean, if we have the infinity of them, still this one is corrected. So for 3 cases, if we have 3 events, still the probability of their union is equal to the addition of their probability and minus the probability of their intersection, the joint intersection of them, and at the end we add the value of their probability together. It's very easy to prove this theorem by looking at the shape of the cases that we have it there. If you just take a look over here at the shape that we have it for 3 events, if I shade the probability of the events A then if I use the green color, as you can see, it contains all these 4 parts. For the probability of B, we have this one. This part is repeated 1 times more, and for the probability of C, we have these 4 parts as well. As you can see, the part in the middle counted 3 times, and when we remove the joint actually intersection, it's remained that we should add this part at the end to the total. So let us take a look at the next slide as well right now. So at the next slide, we have a note that the probability of some events are given. Before that we continue to take a look at the note 1, we should emphasize about the subtraction of 2 sets. When we subtract the set B from A minus B, we use this symbol, the slash symbols, to determine the subtraction of 2 sets, and it's as the same as A intersected by B complement. What does it mean? If you just take a look over here, I just sketched 2 events over here in a sample space, and this is the set A, and the set B complement, the set of B complement is containing all parts that is not inside of B. Means that this part and this part totally will be the B complement, and the intersection between this green part and the pink part that we have it for A will be this part indeed. So means that the probability that we have it, the shape that we have it over here contains the A, all the events of A minus the set B. So A minus B or A slash B is equal to A intersected by B complement. So if we can see visually any type of the relation between the events, then simply we can convert these things to the probability rule. For instance, over here, let me just focus on a first condition that we have it. The probability, if we want to prove that one by using the additive rule, it's simply can be done over there. What do I mean? We have the probability of A minus B, probability of A minus B, and it's said that the probability of A minus B is equal to the probability of A minus probability of A intersected by B. Let me just shift that intersection to the left side. So then I have this relation, means that probability of A intersected by B should be equal to the probability of A. This is the things that I want to prove it. If I prove this relation, then the note 1 will be proved as well. Means that this one that I put an arrow on it. So it simply can be proved by take a look at the shape. So if I consider one sample space like this and put 2 events like A and B with the even with the intersection, so they are not disjoint. It's a normal case that we can consider it. Right now, A minus B, let me just use the pink color to shade the A minus B, and the intersection of them also is here. So as you can see, the intersection and A minus B are disjoint sets or disjoint event or mutually exclusive. As you can see over here, let me just put the marker over here to show that this part is their intersection. This is the A intersected by B, and the another part, the pink color, as I said it, determine the A minus B. They are totally disjoint, and based on the additive rule, I can say that the probability of their union, because they are disjoint, is as the same as their addition of their probability. So means that the probability of the union of A minus B, let me just write it over here, A minus B union by the probability, the set of A intersected by B, this probability should be as the same as the addition of their probability, because they are disjoint. So it's equal to the probability of the first one plus the second one. It's as the same as the expression that we have it over there at the left side, means that it's as the same as this. So but if you take a look over here, the union of these two sets is as the same as A. So as you can see, this is the A, the union of this pinky and gray part will be equal to the probability of A. So we already prove it by this way. If you just take a look on it, we prove the first notes. But instead of proving all this type of the thing, you can take a look on it, and by visually, by looking at the Venn diagram, you can find this formula. This A minus B is a pink part, and this gray part is A intersected by B. And as you can see, the addition of them, if I just put both of them in one box or in one bowl, then their union will be equal to A. So the probability of A minus probability of their intersection will be the probability of A minus B. It can be true for probability of B minus A in the same way. If you just swap the place of, interchange the place of A and B, then you have this formula. And the third and fourth formula in our notes totally coming out from the idea of the De Morgan rules. So if you remember the De Morgan rules, the De Morgan rules said that the probability of the union, the union of the set, if you have a union of the set like A union by B, and if I calculate the complementary part of that one, A union B complementary, is equal to probability A complement intersected by B complement. This will be the De Morgan rule, the first De Morgan rule. So right now the probability of left side and right side should be as the same. And again, I can use that concept that the probability of A and the probability of A complement, the addition of them should be equal to 1. Of course, you can see that the A and A complement are disjoint or mutually exclusive. As you can see, there is no intersection between one set and the complementary part. And because they are mutually exclusive, I can say that the probability of their union, means that A union by A complement should be equal to the addition of their probability, means that it's equal to the probability of A plus probability of A complement. And of course, the A union by A complement is as the same as the sample space. So the left side, inside of the left part, means that this part can be replaced by S, and based on the axiom, we can say that the probability of S is equal to 1. So let us solve that example to see that how can we use this contents over there. So first, let us take a look at the first example. It said that what is the probability of getting a total 7 or 11 when a pair of dice are tossed. So I just sketched the shape of a pair of dices over here. So you can see we have two die here, and the pair of dice are tossed or flipped, and one number is coming out. As you can see, there is 6 number that can be written at the die over there. So that number could be 1 2 3 4 5 6 or 1 2 3 4 5 6 for the first die, and for the second die we have that values. So I sketched the sum table, means that for instance, if the first die is 1 and the second one is die, then the sum of that number, the total number that is coming out, will be 2. So indeed, if I want to sketch the sample space, as I said, the most important part is describing the sample space correctly. So the sample space contains all two elements like X and Y, which determine the position of them, where I can write it like this, X and Y, such that the X is a number between 1 and 6, because there is 6 sides for the die the first die. And also for the second one, for the y also, I have the value between 1 and 6. By this actually description of the sample space, I can say that there is 36 cases, because as you can see, the sample space contains of two places. It's ordered paired, that I have 6 cases for the first one and 6 cases for the second one. So the total of that one, based on a multiplicative rule, will be 6 times 6 or 36. So I have 36 elements in our sample space. If I want to describe them by the elements over there, it will be 1 and 1, for example. The next one is 1 and 2, so it's going forward up to the end, 1 and 2. Then the next one is 1 and 3. Then the next one is 1 and 4, 1 and 5, 1 and 6, and then 2 and 1, 2 and 2, and 2 and 6, and it's ended to the 6 and 6. It's important to understand the sample space clearly, and for each of them I have one addition, means that the addition of 6 and 6 is equal to 12, as you can see over here. The addition of 1 and 1 is equal to 2, and I put all of them in a sum table, the summation of the numbers. So the question asks you that what is the probability of getting 7, or the words over here is very important, or 11. So the number 7 can be laid on a diameter over here. You can see that all the values 7 are here. It's 7 in this case, and all the value of 11 are here, and I just circled them over there. So if I consider all the cases over here, the 7 occurred or 11 occurred, then we have 1, 2, 3, 4, 5, 6, 7, 8 cases, 8 out of 7, 1, 2, 3, 4, 5, 6, 7, 8 cases out of 36. So we can write it like that, but we just try to use the additive rule as well. So for this reason I define 2 actually events. So let me just define that 2 events over here. If I assume that the events A determine the cases, let me just write this explanation over here. If the event A is an event that the total of numbers will be equal to 7, and let us define the events B as well. The events B, let me just write it over here. The events B is as the same, I mean the events that right now we have the total number, so event, it will be event that the total will be 11. So by that 2 events that I define it, I can find their probability as well. First, the events A and B has no intersection. There is no intersection between A and B, because the total 11 has no intersection by a total of 7. So they are mutually exclusive. There is no intersection between them. When there is no intersection between 2 events, they are mutually exclusive, then the probability of their union will be as the same as the addition of their probability. Means that probability of A union by B is equal to the probability of A plus probability of B. So this will be the value over there. And in a question they ask you that to find the probability of getting total 7 or 11. So that's the key. When I said or 11, means that I'm looking for the probability of their union. I'm looking for the probability of union of A and B, and it's going to be the probability of A plus probability of B. Based on a question that the things that we have it about the probability, I should calculate the cases that the addition of a number are 7 and I divide that value by the total cases. So the total cases, the total elements of sample space is 36, and the cases that we have, the addition of 7 is equal to 6. So I have 6 over 36, or 1 over 6, plus the cases for B is 2, because we have 2 cases only that the addition is equal to 11. One when the first die is 5 and the second die is 6. The another one when the first die is 6 and the another one is 5, as you can see. So it's going to be 2 over 36 and or 1 over 18, and when we add them it will be equal to 8 over 36. And if you simplify that fraction, the result will be 2 over 9, as you can see over there, if you divide it by 4. So simplify it by 4, then it's gonna be 2 over 9. So as you can see, if we describe the sample space clearly, if we understand the sample space clearly, then we can solve this question even without sketching all that type of the shapes over there. So let us take a look at the next question, which is my favorite question in this case as well. So as you can see in this question, in a random experiment, it is known that the probability of A is given by 0.35, their intersection is 0.19, and A prime union by B prime is 0.15, and they ask you to calculate the probability of B. To visualize the question, I sketched the shaded part over here. The first one determine the set A, the second one their intersection, and the third one is A prime, A complement intersected by B complement, which is based on the Morgan rule is equal to A union by B totally prime. Let us start from the last concept, means that we have the De Morgan rule, and let us use that De Morgan rule to see that what do we have. So if I just take a look over there, we have 0.15, and this 0.15 is as the same as the probability of A prime or A complement intersected by B complement. So if I start from this point, I can simplify that expression a bit. So means that we now from the De Morgan rule, the probability of that one is as the same as the probability of A union by B, and instead of that prime, I just put the prime outside of that expression, means that we have the probability of this expression. And from the theorem, we remember that if we have a prime of something, I can rewrite that one as a 1 minus probability of that case, means that 1 minus probability of A union by B. I can rewrite that expression like this, and right now I can apply the additive rule. If you remember that the probability of the union of two sets is equal to the probability of the first one, I just split it like this, plus probability of the second one, because we have a negative outside, it's affect both of them, minus probability of their intersection, when over here it becomes the addition of their probability. So it will be the probability of A intersected by B. Right now I have the value for them, and the unknown value remains over here, means that the probability of A is given by 0.35, and the probability of B is unknown. The probability of their intersection also is given by 0.19. So right now I can calculate the probability of B. It's only enough to shift that expression to the left. Then I can also shift that 0.15 to the right side of the expression. Then I have the probability of B at the left by shifting that probability minus probability of B to the left. And as you know from the high school knowledge, when you shift an expression to the other side, the sign of that one will be changed. So we have 1 minus probability of A is given by 0.35, and we have also plus 0.19, and also that 0.15 shifted to the right side, and we have minus 0.15. So if you found some value, some probability as a negative value, means that you made a mistake in some part, or that type of the condition cannot be true. So you should care about it. I emphasize it in a classroom most of the time, that check your steps. If you find the probability negative, means that something is wrong. It's impossible to have a negative probability based on the axioms. So now let us take a look at the conditional probability. The conditional probability is the probability of one event occurring with some relationship to one or more other events. That means when one event occurred already, and we want to know what is the probability of the other events based on this condition, then we have a conditional probability. We use one symbol for that type of the probability, means that we use the symbol like this. The probability of A in a condition, this vertical line is read in a condition, means that when I just put that symbols, that vertical line inside of the probability, means that in a condition that the B is occurred, has been already happened. So when I want to calculate the probability of one event like A, with that condition that the event B has been already occurred or happened or appeared, then this gonna be the conditional probability. When we have a conditional probability, to calculate that type of the probability, instead of that vertical line, I just curve the line and write it like this: A intersected by B. Instead of that vertical line, I curve it and I will write it as a probability of A intersected by B, and I divide that expression by the probability of B. Of course, the probability of B cannot be 0, means that B cannot be impossible events. In a case that the B is impossible events, or the B is empty set, then the probability of B is equal to 0. So that cannot be happen. So I emphasize about that the probability of B is not 0, and the B should be a possible event. So with that condition, we define the conditional probability. We have one example over here. Event A is that it's raining outside, and it has a 0.3 or 30% chance of raining today. Event B is that you will need to go outside, and that has a probability of 0.5 or 50%. A conditional probability would look at these two events in relationship with one another, such as the probability that it is both raining and you will need to go outside. So as you can see over here, we have this relation in a conditional probability over there, and the formula for conditional probability, as I said, it will be the probability of A and B over the probability of A for B in a condition of A, and instead of the and in the middle of them, you can put the intersection as you know before. So now let us take a look at one example for that conditional probability. The question said that the probability that a regularly scheduled flight departs on time is probability of departure is equal to 0.83, as you can see over here. And the probability that it arrives on time is 0.82, and the probability that it departs and arrive on time, look over here, it's important to see that joint words, I mean the and, it's given by and, it's not or. So if it was or, means that you should consider their union. The probability that it departs and arrive on time is probability of D intersected by A is equal to 0.78. I emphasize again about this situation that we have two events, one departure on time, that is 0.83, and one arrived on time, that is 0.82, and the probability that these two events happen simultaneously in the same time is equal to 0.78. We have two actually question over here. So the first one said that we want to find the probability of arriving on time given that it departs on time. Means that when we said it's given that, it means that the second part has been already done. So by the another word, at the part A of this question, I want to know the probability of arriving, this is the probability of arriving on time in a condition, given that means that in a condition that it departs on time. So the probability of A in a condition of D. So of course it will be the probability of their intersection, A intersected by D, divided by the second one, means that divided by the probability of D, and the value are given over there. Simply you can put the values of that things, means that the probability of their intersection is 78 over 100, and the probability of denominator is the departure, which is 83. And for the part B, as you can see, we have the probability of departing on time. We want to find the probability of departing on time, means that the probability of even D in a condition that it's arrived on time, so in a condition of A. So it's equal to the probability of D intersected by A, which is no differences between them because it's associative. You can write it A intersected by D instead of D intersected by A, over the probability of A. And again, by that things that we have it, I mean their intersection again is 78 over 100, and the probability of A or arriving on time is 82. So we have this value for a part B. So right now we have one example. With that example, I think that the concept of additive rule and the union of the probability and also the conditional probability will be clear more than this. So in this question we have a table, that in a table one population was studied, and based on the study of that population we realize the number of the people are totally like this. I mean, we have 5 male who are smoker and 3 female who are smokers, and we have also the non-smoker 20 male and 35 female. So based on this information means that we have a population of some people that we studied all of them. We want to answer to some question. Before that we continue to read the question, I prefer to add the value to see that how many person do we have in this study. For this reason, let me just extend this table and put the summation notation over here to add the cases. Means that all smokers that we have, it is 5 plus 3 or 8 cases, and all non-smokers are 55 persons. So for the case that we discuss about their gender, we have 25 male over here, so we have 25 male, and also we have 38 females. In that study we have this population, and together I can find the addition of them. I mean 25 plus 38. So if we just consider that one, 8 and 5 is 13, and we have 63. So we have 63 in total, the population that we study. So we select one person out of this population, one person is selected, and over there I want to note the probability of something. As you can see, the probability that the given person is a smoker, female, a smoker, and female, a smoker or female, or some conditional probability over here. Before that I continue the question, I want to name two events over here. One event that I define it by F means that this is the event of being female. So the event of being female is given by this F, and I just put one more words for the smokers. Based on the question, I just use these two events. So it's the event of being a smoker, the selected person indeed. I just try to somehow summarize that event's definition. So I have two words over here. One is used for female, one for a smoker. So the first thing that the question asks is finding the probability that the given person will be a smoker. Means that I'm looking for the probability of S being a smoker, and based on that one I just count the number of the smoker, which is 8, and I should divide it by the total, which is 63. So the result will be 8 over 63. So I have 8 over 63 for these cases. So the probability of being female means that I should count the number of females over there, and simply you can find the number of females, which is 38, and you should divide the number of the females, which is 38, over the total, and the total are 63. So we have 38 over 63. The next question asks you to find the probability that the given person will be female and smoker. Means that when I just use the word and, it means that simultaneously both of them should be occurred. By the other words, that word and determine the intersection of these two events. Means that I'm looking for the probability of being female, so I will put female, and because if it's an and, I just use the intersection by the being a smoker, so the probability of being female and being a smoker. So the female parts are here. I mean, this is a part of a table belongs to the females, and the part of being a smoker is here as well. As you can see, the intersection of these two boxes determine the people who are smoker and female in the same time. Means that it will be 3 cases out of 63, the total cases that we have it over there. So the result will be 3 over actually 63. This will be the probability of being female and smoker in the same time. In the next part, we ask you to find the probability that the given person be female or a smoker. When we use the word or, as you remember that, it means that we are looking for the probability of the first events being female that we determined by F, union by being a smoker. So because it's or, we use a union over there, and based on an additive rule, this expression is equal to the probability of the first one. Means that probability of F plus probability of the second one, probability of being smoker, minus the probability of their intersection. So minus the probability of their intersection, which is F intersected by S. That's gonna be the case over here. And over here, if you just take a look at the value that we had it at the part 1, 2 and 3, we have that values. So the probability of being female was 38, so it will be 38 over 63, plus the probability of being a smoker was 8, So the total probability of being a smoker is 8, and we should subtract their actually intersection, which is 3, and the result should be divided by 63, of course, and we will find the value. But if you just take a look at that table, you can find the interesting things. So as you can see, this is the female part, and this part is being the smoker. If I want to count the cases of being a smoker or female, means that I should add this 5, 3 and 35 together. But when I just use 38 over there, means that I add these two values, 3 and 35 together. And when I use that 8 over here for the smoker cases, I count this intersection 2 times, means that I add 3 and 5 together. So I should remove these things, and for this reason that 3 is removed from the addition. By the other words, when we have these cases, we can already use the another techniques to calculate this probability, means that I can rewrite that one as a 5 plus 3 plus 35. These are the cases that should be added. If I want to avoid to repeat that part, I can simply add these numbers and divide it by 63. Of course, the result will be the same. So for the next case, they ask you that to find the probability of being female, given that, means that we have some condition over there, given that the given person is a smoker. So I'm looking for the probability of being female, given that the selected person is a smoker. So based on the definition that we had it for the conditional probability, we have the probability of F intersected by S, the probability of being female intersected by being a smoker, over the probability of the second one, means that the probability of being a smoker. So we have the values over there. The probability of their intersection was 3 over 63, and the probability of being a smoker is calculated as 8 over 63. So the result will be 3 over 8. But this one also give you one inspiration, one idea about that what we gonna do over there. So when we said that it's given that the person is a smoker, means that we are totally working in this part of the table. This part of the table is considered. And when we said that what is the probability of being female with that condition, means that the first one is occurred, it has been already occurred, means that we know that the given person is a smoker. Right now the probability of being female is 3 out of the total over here is 8. It will be 3 over 8, and as you can see over here, the result at the end after applying that formula is 3 over 8. That's the interesting part, means that when some events occurred, has been occurred actually, then we can say that okay, we have that part only, and we are looking for some event in the heart of happening of the another one. So that's why we can write that expression like this. For the second one also we have the same situation, means that we have the probability of being a smoker. That's the question, given that with the condition that the given person is female. So by that one, again, by the definition of the conditional probability, we have the probability of F intersected by S, the intersection. I remove the vertical line and I put the sign of actually intersection, and I divide it by the second probability, which is probability of F. And based on the previous part, we know that the probability of their intersection is 3 over 63, and the probability of being female is given by 38 over 63. and again this 63 is cancelled from the numerator and denominator, and the result will be 3 over 38. So this 3 over 38 determine these things as well. If you just take a look at the question at the table, it's given that the person is female, means that we have already known that the person selected from this part of a table, we know that the person is female, means that it's selected out of this 38, and being a smoker over there is 3 over 38. We can talk about the negation of them. For instance, we can say that what is the probability of will not be a smoker, means that non-smoker cases could be asked, and you can see that that type of the things is done over here, means that the probability of S prime or not being a smoker can be considered as 1 minus probability of S. You can use this concept to calculate the complementary of some event as well. However, over here it's very easy to find it because you know the non-smoker is 55 out of 63, so you can find it directly by using that one, which is 55 over 63, or you can subtract 8 over 63 out of 1, which is equal to the same thing. So I just finished the lecture over here, and we will continue the discussion for the next lecture. Thank you for your attention.